Start the recording now. All right, so glad to see everybody here. Well, I'm glad to see those who came here, and we're going to go ahead and get started. So we're going to start off with antennas and feed lines. We're going to move on to amateur radio. Well, I can't remember what the next section is called, but it's waveform characteristics or something like that. But anyway, we're going to go ahead and get started here. And first, we're going to take a look at how antennas work. And I did do some testing this week to see if I could get Bob's original slides to work with this OBS 2. And for some reason or another, it just won't record on there. It won't record the video. Yeah, actually, I've got a hotkey set up for that. Let's see. Hold up. OBS. So see, we are recording. Yeah, it says, see, it says stop there. So we're recording. I've got a hotkey set up for it so that I don't have to have the OBS open to be able to start the recording and stop. I've got record, stop, pause, and unpause. I put pause and unpause on there because I've got a whiteboard and I'm building a stand to hold a camera up here so that I can use a whiteboard below it and put the whiteboard on there. The thing is, I can get it to switch over for the recording, but I can't figure out how to get it to switch over so it shows on there. Well, yeah. Mm-hmm. Okay. Oh, yeah, there's a YouTube video, and there, I guess the how do antennas work? Ah, okay. Yeah. That isn't that? I don't know. It doesn't work on this program, no. Because I'm using, I can't figure out how to get the OBS to work with the LibreOffice. So I'm using the PDFs instead, and I guess the links don't work on. Control, click what? No. No. Okay, so anyway, yeah, the video is real good. I can't remember the name of the company that did the video, but that's probably, yeah, okay. And I used to work for DirecTV. Well, I used to work as a contractor for DirecTV. Okay, so antenna types. There's a dipole antenna is probably the most common and the simplest form of antenna. Here we go. All right, so the dipole is probably the most common and the simplest form of antenna that there is to work. And this is a type of dipole, even though it's only a quarter wave, that you actually have a physical antenna. The other quarter wave is an image from the ground. So you're usually going to be using ground radials, or in the case of you put a quarter wave antenna on your car, it uses the body of the car for the ground reflection to provide the other quarter wavelength for it to work. The ocean, yeah. The water the salt water in particular is probably the best ground plane you can find. Just the thing to keep in mind with these is that quarter wavelength. So you're looking at a 40 meter frequency. 1/4 of that wavelength is going to be 10 meters long. 10 meters is 32.8 or 33 feet. So that's a pretty tall antenna that you would have to put in order to use 40 meters on a quarter wave ground plane. So I do have an antenna that I can use on a couple of different frequencies. It's 17.5 feet, so it's not that tall. And it has ground planes, and I've been able to make I get a good SWR on it for 10 and 20. And I think one of those in the middle, there's 12, 15, and 17 in the middle. I think I can get a good SWR on one of those, but I can't remember which one. Yes. Okay, so as far as the test goes, it would be a good idea to remember the frequency range of each of the bands. Remember I said that when you're doing these math questions on here, any of these math questions, they'll never give you an answer that's outside of the answer will never be an answer that's outside of one of the bands. It's always going to be inside one of the bands. Now, there is a little fudge factor because remember last week we said that the bands, so like 40-meter band is, they call it that because it's close to 40 meters. It might be a little less, it might be a little more, but it's fairly close to 40 meters, and it's just easier than adding a decimal point and a bunch of numbers after that. The simplest way that I found, I never memorized all the bands. Now I'm kind of getting used to them now because I've been doing this for a little bit. But in the beginning, I didn't memorize any of the bands, what the frequency ranges were. Except there on one test, I can't remember, it might have been two tests, there was a couple of questions about, is this in this particular band or not? And then you have to know. But even then, two of the answers are way outside, and then two of the answers are close, but only one of them is closest.
About what segment of 10-meter band can a technician operate in? That you should know.
Yeah. And that's for voice, and it's going to be 10.3 or 28.3 to 28.5. So the thing that I did for all of these on a technician test, all of these parts like this, I just looked at the band. So if it says it's a 40-meter band and it wants to get a quarter wavelength, then you already know a quarter wavelength is going to be 10 meters. You already know 10 meters is roughly 33 feet, and there's your answer. Now, it may ask for the answer in inches, and then you'd have a little more calculation to do, but that's fairly simple. So, howdy, David. We will discuss, is that it covered in technician, SSTV? I don't think there's any part in the technician. Yeah. Yeah. Yeah, we get kind of, we've been through all of them so much. But I don't think there's any SSTV privileges for the technician license. So there, I don't. Yeah. Yeah, because everything above, I think it's all VHF and above is you covered. I'd have to look at the chart again myself. But yeah, I don't think you'll see anything about single or slow scan TV on here on the technician. If we do, we haven't covered it yet. So if it is, we are yet to cover it. So anyway, 1/4 wavelength, David, above the Earth's surface for a vertical quarter wavelength ground plane antenna. The other quarter wavelength is an image below the ground plane. So you have to have, with that type of antenna, you have to spread out some radials. So, all right, the half wave dipole, this is the one that most people are familiar with. It goes up in the air, horizontal rather than vertical. Your center conductor is connected to one side, your ground or your shield is connected to the other side of the antenna. This antenna can be used if you cut it so that it's resonant for the frequency that you want. It can be used without any other articles between it and the radio other than your feed line. A lot of folks will use on these. They'll put a choke right where it connects to the feed line, just so that it doesn't go down the feed line. But it's not 100% necessary. I've built a 10 meter dipole antenna, and it was fairly simple to build. It you don't have to wind anything. It's just 2 wires, a connector, and a feed line. But when you go to tune it, make sure that there's nothing close that it can couple to, because if it couples, it'll throw off your tuning. And I ended up cutting way too short, and there's one thing for certain. When you cut it too short, it's harder to add length, because then you have to start soldering, and then you have bare exposed wires. So when you're cutting it, cut little portions at a time rather than big portions. The 2 ends have to be equal. So if you cut a 1/4 inch off one end, you got to cut a 1/4 inch off the other end if you're starting with the equal length on each side. Yeah, everything affects everything. So copper wire works best. Stainless steel wire, I had talked to one fellow that said he was using stainless steel wire and couldn't figure out why he wasn't radiating well. Something about stainless steel, it just doesn't work well for a radiator. So, but yeah, copper wire. So most people that build these just buy speaker wire. So you got 2 wires, you cut one length and then split them, and then you've got 2 equal length wires. And that's actually the way that I've made all of my dipoles. So. Yeah.
Why you usually use copper, or in case of shorter antennas, made out of aluminum.
Yeah. Like this one right here. We'll talk about that one momentarily. Anyway, half-wave dipole measures close to a half wavelength from one end of the antenna to the other. They can be quite long. So remember your 40 meter vertical antenna is 33 feet tall, but your 40 meter dipole, horizontal dipole, is 66 feet. So you have to have some room to stretch it out and pull it up a little bit. And ideally, you want it to be half wavelength high. So your 40 meter antenna, for the best performance, should be 33 feet high. And it's kind of hard to get something 33 feet up. So my 40 meter end fed is 18 feet up, but it works. It would be better if it were 33 feet up, but it's not.
That's the second law.
Yeah, height.
Any antenna is better than no antenna.
Yeah. All right, and normally mounted horizontally between 2 vertical supports. I have 2 very nice nature-supplied vertical supports in my yard. One of them is a queen palm, and the other one is an oak. And I have a rope on pulleys going to each one of them, and then tied off to the ground with a little spiral down there, like you would attach your dog's lead to. Which, by the way, you're not allowed to do. Yeah, for camping, it's fine, but for unattended use, you can't tether your dog. You have to be watching them. But you're okay. So you got the vertical supports. I got it up there. I can lower it from each end. I can lower it down so that I can do maintenance. So I can swap it out and put a different antenna up there, and then pull the rope back up, and it pulls the new antenna back up, and everything's good. And that's your half-wave dipole. This is called a halo, which is a type of dipole antenna. Is this a shorting strip or a match of some sort? Okay. All right, and you'll notice that it says in order for it to be a dipole, it has to have 2 sides, right? So you got this side over here and this one over here, and you'll notice it says there's a 1 3/16 inch gap there where it's not connected, and that makes it a dipole. There is actually another dipole that's all the way around. We'll talk about that at some point, maybe. Antenna types, dipole, orientation. Antennas radiate better in some directions than others. And I think I mentioned this about my 40 meter end fed at one time. I have power lines running behind my house, and somewhere along the line, somebody told me if you have power lines close, suspended power lines, run the antenna perpendicular, and you'll get less interference. So that's the way I set it up. But the way that puts my antenna is in an east-west orientation. Since the antenna rotates or radiates broadside to the element, that means my radiation pattern is more north-south than it is east-west. But I've still managed to make Europe and a couple of Eastern Bloc countries. I've still managed to make Puerto Rico. Puerto Rico is easy, actually. Puerto Rico, it's easier to talk to Puerto Rico than it is to Los Angeles. Not that there's anything in Los Angeles I want to talk to. But anyway, for example, there you'll see what it says. Kansas, basically central point in the United States. You may want your antenna to run north-south, because if it runs north-south and it radiates broadside, that means you got coast-to-coast coverage. So the antenna will then radiate best east and west, meaning that you'll be able to cover most of the U.S. And there's your dipole radiation for a vertical and for a horizontal. There you see how the radiation pattern goes. And it's a good thing I had lunch today, because that really kind of looks like a donut, doesn't it? Yes, you can. 70 centimeter. Okay, the higher the frequency goes, the more the leaves will affect it. So I bought materials to make a 2 meter called a roll-up Slim Jim. So it's made out of window line. It's a twin lead that's 1 inch wide, 450 ohm impedance. I bought enough to make 2 with a little extra so that I could adjust where the antenna begins and ends, because there's certain features of the antenna that need to be on the solid section, not on a window. So I had all that in my mind. I was really going. I thought I had this whipped on the first try. Cut it in the wrong place. And then ended up with the gap. There has to be a gap between the radiating side and the matching element. There has to be a 0.81 inch gap. And I cut it on the window. And as soon as I made the first cut, I said, man, I was not supposed to do that. So anyway, I had it. It was already done. So I'm going to cut the top part of it loose and make that into a 70 centimeter. Now, the thing is, with the 70 centimeter, for the 440 band, that is affected by leaves and vegetation. So I'll have the roll-up Slim Jim to use for that, but I'll most likely have to put it on a fiberglass pole to raise it up. But the purpose of the roll-up Slim Jim is it's an emergency antenna, and everything that's going on there in the Appalachian has inspired me to finish this project, even though I've had the materials to do this for like 3 months. But, you know, everything that's going on there inspired me to get this done. In case that next one comes this direction, I'll have it. So basically, I'm building the antenna. When the antenna's done, attach a rope to one end of it, throw a rope over a branch of a tree, 20, 25 feet up, and pull it up. And then all of a sudden, you've got an antenna that's 20 or 25 feet up in the air to make communications. When a storm like that comes through, obviously those who have antennas and don't want to have to replace them are going to try to take them down, and they've probably already given some consideration to how they would get them down in order to save them, so that it's a quick and painless matter. Anyway.
As you bring it down close to the earth, then kind of the bottom half of that goes away.
Right. And instead of being, spread out in an even donut, it would start the parts, as it gets closer to the ground, those parts start to come up, and it'll radiate elliptically out to the sides. So, but yeah, with the 70 centimeter, I would have to put it up on a fiberglass pole. And it's a, something fun to do. And then hopefully hopefully I'll never need it, but if we do, I'll have it. The thing that they're experiencing up there right now is all the cell towers are out. Even the police and the highway departments, all of their communications is out. So nobody's communicating with anybody. The only way in or out of that area there is by amateur radio, and amateur radio operators are working overtime right now on a volunteer basis, trying to get messages in and out to, from the people there that are impacted to their loved ones outside. So it's a pretty big thing. All right. So antenna types, let's see, polarization. So, this is actually why when I was started to look at this earlier in the week, this is the slide right here where I decided I needed to try to get the OBS and LibreOffice on one page together and try to get them to function, but they won't do it so far. I'm going to still work on it some more, but this graphic goes back and forth. So you'll watch this, the voltage there, it'll come down here and become negative, and this one here positive, and goes back and forth at the same time that this one here is moving back and forth. So you get to see the action of the voltage on the antenna radiator and the E field there. And this particular one doesn't show your magnetic field. And then polarization, this is the point of this before I get away from it. Polarization is the E field with respect to the Earth's surface. So when the E field is laying flat like that, then it means it's horizontally polarized. And if in the air, then your E field is going to be standing up, and it would be vertically polarized. And I have heard different things about the transmission lines, that they actually are polarized one direction or the other, but some people say one thing and other people say something else. So, and there we see you've got linear, circular, and elliptical polarization. So this is before it hits one of the layers of the ionosphere, and these are after it hits. Typically, this is what you're going to get after it contacts one of the layers in the ionosphere. David here went and bought the book. That's pretty cool. Yes, he will. Anyway, which of the following describes a simple dipole-oriented parallel to the Earth's surface? Not vertical, but parallel. I just gave the answer away, didn't I? Horizontally polarized. Okay. In which direction does a half-wave antenna radiate the strongest signal? In which direction? And you notice it says strongest. Broadside to the antenna, that is correct. So remember I said, my antenna radiates better north and south. So I've talked to Canada several times, and I've talked to various places in South America from time to time, but it does still reach east and west, just sometimes better than others. Wavelength. We're going to talk about calculating the wavelength now. And you've got a few things here, and actually some of this we've already went over. You know that the upside down Y is the wavelength symbol. You know that the C is the speed of light representation. And you know that the speed of light is roughly 300 million meters per second, which we represent as 300. We do the 10 to the 6th thing, and then that makes our answer in megahertz rather than it makes it in meters or megahertz, depending on which direction you're going. There's another variable that we're going to add in here. The signals travel in bare copper wire at approximately 0.95 the speed of light. So if the speed of light is 300 million meters per second, 0.95 of that is how fast the wave, remember, that's traveling in free space. And my lodge in free space is not quite completed yet. It's still under construction. But that's the way it travels in free space, and then you get inside the atmosphere, it travels a little bit slower. You put it in copper, it travels a little bit slower. You put some insulation that says bare copper. Okay, remember the parts in red are important. Bare copper is 0.95. You put a little bit of insulation around the outside of it, it slows down even just a little bit more. I was just telling you about the roll-up Slim Jim antenna that I'm making out of the window line. The window line has a velocity factor of 0.91. I got that off the manufacturer's website. Or actually, not the manufacturer, the distributor's website. The length of a dipole antenna is actually 5% shorter than what you calculate, because when you calculate it, you're calculating it for out in the atmosphere. So it gives you that formula there at the bottom. The wavelength is equal to 0.95 times the quantity of 300 over the frequency in megahertz. And the 39.4 there is a number of inches per meter, 39.4 inches per meter, because some of the questions will require you to convert the answer to inches rather than meters, because they know that that's how we're going to build the antenna, is we're going to measure in inches, because that's what all of our tools do, is measure in inches. Now, if you're me and you went to school where I did when you were younger, you would remember that, well, if you're me, you went to school where I did and you had the same birthday as me, it would be easier for you to remember that meters converted to feet is 3.28. So 3.28 feet per meter. And then you just have to do the inches by adding the 12. But Bob gave us this one. So if you can remember 39.4, it saves you a step in the calculation. Okay, so let's calculate a length here real quick. So for a 70 centimeter dipole, you'll notice that the frequency of 444.925 megahertz was chosen there, and that is the KSC repeater, right, up on the VAB. So that's an actual local frequency that you could tune in and listen to on Thursday nights at 7:30. So 70 centimeter dipole is, so 0.95 times 300 over 444.925 ends up becoming 0.64 meters. And then if you do the math with the inches, 39.4 inches per meter, you would come up with 25.24 inches. And remember that that is a whole wavelength. That's a whole wavelength. And if we're looking for half wavelength, we're looking at 25.24 over 2, so 12.6 inches would be your half wavelength. And then you want to carry it further for a quarter. If you're going to measure, get the length of the two quarter wavelength legs, it would be 6.3. For 2 meters, this is a 2 meter Yagi right here. And this element right here is the driven element, and it should be roughly, I think 38 or 39 inches, something like that, from end to end. Each side is a quarter wavelength, so about 19 inches or so. So for 2 meters, let's say, okay, and in this case, we're looking for a quarter wavelength. Let's see. Okay, so 2 meters over 4, because we want a quarter wavelength, becomes a half meter. A half meter 39.4 times 1/2 becomes 19.7 inches. So just like one side of that, 19.7. So your quarter wavelength, and then you multiply it with your factor, and I don't honestly know what the factor is for aluminum. I also don't know what the factor is for aluminum that's got splotches of paint on it. That's probably different. And the diameter, and we've had this discussion about the diameter before, and we haven't really been able to pinpoint why, but it does. So anyway, so you're when you take your factor for bare copper 0.95, it becomes 18.7 inches. 10 meters, so 10 meter half wave, 10 divided by 2 times 39.4 comes out to be 197.1 inches. And then the bottom line there draws out all the numbers for you, or for the 95 for your velocity factor. Okay, what is the approximate length in inches of a half wavelength 6 meter dipole antenna? So use the 6 and plug into the formula for 1/2 wavelength. So 6, it's got to be 112, right? So 6 meters, you want 1/2 wavelength. You know it's going to be 3 meters. 3 meters times 39.4 would give you something above, a little bit above 112. And then when you do the 0.95 velocity constant, I think it gives you actually gives you 112 point something, if I remember right. It was earlier in the week when I looked through it. And this is one of the things that having the whiteboard would benefit me. Okay, so 112. So here we have half wavelength is 3 meters. 3 meters times 39.4 comes up to 118.2 inches. The approximate length of the antenna will be 118.2 inches times 0.95, or about 112 inches. You notice it says about. Okay, when you build a dipole antenna, it probably won't be resonant on the frequency you want. Remember, everything affects everything, so cut it a little bit long because you're going to have to make some adjustments to it. So for a 10 meter, I cut it about 5 or 6 inches long and then made several cuts, but I was making small cuts because I didn't want to cut it too short again after I discovered what the problem was. To tune the antenna, you need to determine its resonant frequency, and then you make it either longer or shorter to get it to where you want. Now, remember we said that it's harder to make it longer than it is to make it shorter, so that's why we want to add a few extra inches on each end. Like I say, 10 meters, I made it 5 or 6 inches longer on each end than what I actually needed. And when I did the calculations, I didn't do the 0.95 because I didn't have an accurate constant for the speaker wire. So I just cut it 5 or 6 inches longer, and then I made several cuts until I got it down to where I wanted, which was 28 point, I think 28.4 is what I was looking for, and I got it down to 28.45, and I just stopped there. Well, you can fold it back on itself, yeah. Yeah. Okay, so to tune, you make the antenna. Now, so you might ask yourself, well, how do I know if the resonant frequency is high or low? All right, well, that's where they make antenna analyzers that make this all real simple. And if you've got the money to buy an antenna analyzer, then you go ahead and grab one of those. I got Mini VNA, and I think it was like $60. You have to do a little bit more work to set it up. You have to figure out how to read it. Bob likes the VNA. He's got a couple of them. Let's see. The thing to keep in mind is that the length okay, it's backwards, it's inverse. So if you need to make the frequency go up, wavelength needs to get shorter. And to shorten the wavelength, you just cut a little bit off. And remember, you want to cut off an equal amount on each end. So if you want to cut off an inch, only cut a half inch off on each end, because that makes your antenna physically a full inch shorter. And if your frequency needs to go down, that means your wavelength needs to go up, and it's harder to add it on to the end. If you've just folded it over on itself, then you can pull some more out, but much easier to just snip a piece off on the end. Your final length will depend on the height, trees and buildings, people, dogs, whatever happens to be around. I have squirrels. They don't go anywhere near the antennas. They've learned. But anyway, so everything that's around. So remember when I was telling y'all initially about my 10-meter dipole, and I just had it suspended from the same rope that I had the 40-meter end fed on without removing the 40-meter end fed, and I kept wondering why my line was going all over the place, and it was because it was coupling with that 40-meter antenna. So I took the radiator down and let it lay on the ground and pulled it back up with just the 10-meter dipole on it. The line was nice and straight and clean. But trees, particularly metal things, so a lot of people use chain link fence top rail for a mast for their antenna, and that's okay, but there has to be a little bit of distance between the mast and where your antenna begins or ends. So you have to have a little bit of distance there. All right. Which of the following increases the resonant frequency of a dipole increases the resonant frequency of a dipole antenna? Anybody disagree? Okay, Greg is right. Shortening it. When you shorten it, the wavelength gets shorter. When the wavelength gets shorter, it's inverse to the frequency is inverse to the, okay? So the frequency goes up. What is the approximate length in inches of a quarter wave vertical antenna for 146 megahertz? Now you'll note, disregard the bold A. That's not the answer. But you'll notice they put the 112 in there because you just did one with 112. Okay. So what is the approximate length in inches of a quarter wavelength for 146 megahertz? Going to be 19, yes. Okay, and there's your calculation right there. All right, HF antennas can be very long. Loading is a technique. I want to talk to you about your book before we leave today, because I've been giving people the page numbers that I've been putting in the emails are in reference to the PDF copy. So I want to see how they relate to that one. That's what I want to find out, because yeah, sometimes like all of our PDF tech pubs at work, the page numbers don't match up at all. Yeah, because it just gives you total page numbers from the front cover to the back cover, rather than and some of the stuff up front is numbered in Roman numerals and stuff like that. So oh, okay. Okay, let's see. We started today on page 50.
65 begins at 10.
Yeah. Radio, yeah, okay. All right. Antennas and feed lines. Okay, so since you've got the hard copy of the book, the pages may not always match up for you. But yeah, I always give the lines also, or the titles. All right. Okay. HF antennas can be very long, just like the 40-meter antenna that I've got stretched out across my backyard. It's up high enough it doesn't bother my wife, so I did that right at least. Loading is a technique to physically shorten the antenna. Now, when you look at the antenna on Bob's car compared to the antenna on my Jeep, you'll notice that his antenna is at least twice, if not longer, than mine. Mine is very short, and it's bottom loaded because my Jeep does actually go in the woods, and I didn't want to have to replace an antenna every time it whacked against a tree. And on Bob's car, he doesn't have to worry about driving in the woods, so he's got and his antenna works better. But it doesn't have to be replaced every time he goes on a drive through the woods. And his is center loaded also. And the closer you get to the top with the loading, the better the performance is. But it's hard to top load a mobile antenna. It creates a lot of wind drag. So loading is a technique to physically shorten them. Either inductors or capacitors can be used. Inductors are most commonly used. Capacitors less common. In either case, loading an antenna makes it seem electrically longer to a signal at the antenna feed point. And this is one of the sections that I used to have trouble teaching when I was in the Navy, was how the loading works. But it's all done in the math. So, and then at some point or another, is there resonant math in this, in technician? I can't remember. But we did a lot of, we just finished, Bob just finished. Yeah. Yeah. So in either case, loading an antenna makes it seem electrically longer to a signal at the antenna feed point. And here's a little example. So you've got your ground plane at the bottom. You've got a loading coil in here. And the most popular loading coil is a Wolf River coil, but there are others. You've got your feed line coming in and your antenna. Now you'll notice this antenna looks like it's got a point there and a point there where it gets narrower. Those antennas are usually, it's usually a 17-foot that collapses down. It's telescoping. And it collapses down to just a foot and a half, 2 feet long. A couple of people in the club use those. I'm sorry? That is an inductor, yes. So the way this particular one works, I mentioned the Wolf River coil. It's got a collar on it. It's got a coil here, and then it's got a collar on it. And you slide the collar up and down the coil, and it makes contact with a certain point on the coil, and then there's a shorting wire. And that changes your electrical length of the antenna so that you can tune it to whatever band that you want. Yeah. It's very, it's a popular antenna. It's just a little on the expensive side. So, let's see, what did I say? To shorten. Yeah, and when it says you use a loading coil to shorten, you're making the physical antenna shorter, but you're making it appear longer to the radio and to the feed line. Which of the following describes a type of antenna loading? Okay, inserting a resistor is a no. Installing a spring at the base of a mobile vertical antenna to make it more flexible is a no. Strengthening the radiating elements of a beam antenna to better resist wind damage, that would be a no. So by default, A. By inserting inductors, well, it is in the radiating element. It's at the base of the radiating element, right? All right, so the answer was A. Everybody was right except for me. Antenna types, directional beam antennas. So this is a Yagi, or if you want to pretend like you speak fancy speak, I call it a Yagi, but most people call it a Yagi. But that, like I say, this is the driven element. This is a reflector, and this is a director. They've all got names to them, and there can be more directors out there too. And this antenna can be tuned by using this shorting strip right here. You can tune it, you move it back and forth. You got, well, it's got one there. It doesn't have one on the other hole, but it's got a little set screw right there. You just loosen the set screw and you can slide it back and forth to tune it to your preferred frequency. Yep. Yeah, I don't, yeah. So, okay, so you'll notice that it has a beam and some elements attached to the beam. Highest gain, this is the highest, and remember, I don't know if we touched on this before. When they talk about, did we talk about that? When they talk about gain on antennas, you're not actually gaining anything. All you're doing really is directing in one direction. You're using the same amount of power that you had, but you're just concentrating it in a certain direction, just like a flashlight does. And I had a thing all planned out way back when to bring one of my mag lights with me, where you take the top off and you turn it on, take the top off and sit it down. It works like a candle to disperse light. It's the same amount of candle light. It's just being dispersed in a wide area. And then when you put the top back on it and point it in one direction, it's still got the same amount of light, but it all goes in one direction. So you're not actually gaining anything. You're just using what you have to better advantage. Now, the disadvantage to this is that it has to physically be pointing toward, or at least near toward, where you're going to talk. So I had to break open on Wednesday. I had to break open the iPhone, find the compass on there and sit it down on the table away from the computer and the power supply and everything else, and let it settle out. And then once it settled out, I turned it to where QRZ said the W2SDB repeater was. And when I got it pointed in that direction, I knew which direction I had to point that Yagi. And my wife said, "Why don't you point it the opposite direction?" I said, "Well, that would be long path, and that doesn't necessarily work for 2 meters." No, she didn't say that. My wife is my guinea pig. So, in case y'all, when I go over this material, the wife sits down on the couch, the dog sits down right next to her on the floor, and the two of them together listening to my presentation. And she answers most of the questions. For some reason or other, she has no interest in getting a license, even though she can answer the questions, could easily pass the test. I think she's afraid of having to get a pocket protector. That's the only thing I can think of. But anyway, highest gain is your Yagi or quad or a dish. Now, everybody knows what a dish is. That's the same thing. The signal gets concentrated into one specific area. One of the videos that the antenna video Bob was talking about earlier, that is specifically about how the dish collects the power and then directs it to the LNB. You'd be surprised how simple that LNB is when you open it and look at it. Because when I was doing DirecTV installations, I thought that would be a really complicated technical thing inside there. It's not. It's an open tube that the energy goes into, and at the end of that tube, there's a tiny little antenna, and that's it. Okay, so concentrates the signal in one direction. So you're concentrating the signal, so you're making better use of what you have available to you. You're not actually gaining anything. Antenna gain, and you notice they put it in parentheses or in quotations there, increase in signal strength compared to a reference. And your reference is, in most cases, a DBD, which is a dipole antenna. You may see a DVI, which is relative to the theoretical isotropic antenna floating around in free space. Okay, so here's your 3-element Yagi, and these ones right here were built from regular old Stanley tape measure. So they're using a piece of PVC pipe with a cap at each end and making the connection right there. And this is a common antenna to be used for direction finding. So, yep. And while we're talking about Yagis, how am I polarized right now? Horizontally. Vertically. Okay. Close by the radio signals that I'm getting when I use that, it horizontal or vertical doesn't seem to make a lot of difference, especially with the radio that I have, because there's no signal strength meter on there. If I hear it, it's good. If I don't hear it, it's bad. But farther away or with weak signals, it would make a difference. So, and this, what's that? No, there's a calculator for the distance between them, and I don't have a tape measure with me, but I don't know if these are equidistant or not. Usually not, yeah. It's less obvious with this one though. With the drawing here, it's pretty obvious that the radiator and the that your sorry. Yeah, well, this is the director, and this is the reflector, and your active element there, your driven element, is closer to the reflector. But
So the length of the elements and the distance will change the effect of the phase, and that makes it add. And you can
got it? Okay. And what type of antenna is this, Bob? A quad? Okay. Yeah. So with the quad, what is the polarization? Okay.
there on the side, the red is,
Oh,
so it's horizontally polarized.
okay.
Feed it on the bottom, it's vertical.
All right.
And each of those loops, well, your driven loop is a full wavelength. That's one of the differences.
Okay. Everybody get that? So these bars in here are non-conductive. All they are is being used for spreaders, and the lines going around here are a wire. So instead of having just this flat piece here that's doing it, you've actually got a round part. And this driven element, you said, is a full wavelength. Okay. Okay, what is a beam antenna? An antenna that concentrates signals in one direction. And it also works for receive. You receive stronger in one direction either. You will receive off the back, but it'll be way weaker. What is antenna gain? The additional, I'll let you all read them. What is antenna gain? C, the increase in signal strength in a specified direction compared to a reference antenna. And what is your normal reference antennas? Dipolar isotropic. Yeah. Let's see, which of the following types of antenna provides the greatest gain out of those 4 types of antennas? And Yagi D. Okay, so we hadn't really said much about the 5/8 wave vertical. I was watching some videos this week. One guy tested a 5/8 vertical antenna. Isotropic, we said, is a theoretic antenna in free space. The J-pole is similar to the Slim Jim that I'm building. But I don't know if we talk more about that beyond this or not. But the Yagi is the answer. It is the greatest gain. Antenna types, handheld. Okay, handheld VHF, UHF transceivers usually have that short, somewhat flexible antenna. Now, the radio that I brought the other day had a much longer antenna that was way more flexible. This one is flexible, but not a lot. But this is what they're referring to when they talk about the rubber ducky antenna. Not every radio that you buy with a rubber ducky antenna will be able to screw off the antenna. Some of them are fixed. Now, most of them are FRS or GMRS, but they're fixed. You can't take them off. And this antenna, or this radio here, is a DMR 1701 from Bofang. This will work on DMR network when you want to take time to do it. Short flexible antennas called rubber duck antenna. Inductive loading makes them shorter than a full-sized antenna. So this base right here there's tightly wound coil in there that makes the antenna appear to the radio to be much longer than its physical length. So that's a technique that you'll come across later in much better antennas than that. I've got 3 of these antennas, and I've tested all 3 of them, and they all measure just ridiculously different. And one of them is at 2 meters is like 8 or 9 to 1 SWR. So kind of high, but these things only radiate 5 watts, so it usually doesn't reflect enough to cause any damage. Inductive loading makes them shorter than a full-size antenna. They are much less efficient than a full-size quarter wavelength antenna. So it's best to try to get, you can connect an antenna. There's an adapter you can get that'll go on there, and then you can connect another antenna. You do have to be cautious because that connector on the top of the radio will eventually give way to the constant pressure from having a coax attached to it. So you use like a 2 or 3 foot piece of RG316 on there, so it lessens the tension on the connector, and then attach your coax for an outdoor antenna up higher, much better SWR, so you get more out of your 5 watts that way. You just lose the portability. All right, what is a disadvantage of the short, flexible antenna supplied with most handheld radio transceivers compared to a full-size quarter wavelength antenna? A, it has low efficiency. Okay, antenna types. Let's see, using a handheld VHF transceiver inside a vehicle is not very efficient, because not only do you have this inefficient antenna, but you're also inside of a steel Faraday cage. Well, we'll give them the benefit of the doubt that it's steel. It's probably aluminum. But you're still inside of a Faraday cage, which keeps your signal from getting out. The vehicle's metal frame will act as a shield or Faraday cage. The signal strength of the transmitted and received signals will be greatly reduced. So I know people that use those in their cars, but they like I say, they have a thing that they connect to it, and then they have an antenna outside with a mag mount. If you use a mag mount once a week, take it off, clean underneath of it, clean the bottom of the mount, because stuff will seep under there, and you take it off in 3 months and half your paint will be gone. So you have to keep up with that. What is a disadvantage of using a handheld VHF transceiver with a flexible antenna inside of a vehicle? A. Signal strength is reduced due to the shielding effect of the vehicle's body. An externally mounted antenna will work better on a vehicle. The 5/8 wave vertical antenna. Is yours 5/8, Bob, or is that a half? Yeah. The 5/8 wavelength vertical antenna is a popular choice. It has more gain than a quarter wavelength, which is what mine. So roughly 2 dBs greater gain over a quarter wavelength. Elevation patterns, let's see. Which one there is the one with the 4 lobes, the 5/8? Or is that the quarter? I think it's the yeah, I think the one with the 4 lobes is the 5/8 because it's actually reaching out farther, and the 2 lobes is the quarter wavelength. So the reason you would get those 2 extra lobes right there near the top with the 5/8 is because you're not far enough off the ground to let it flatten out. But the quarter wavelength there is still not reaching as far, even though you've got it concentrated into just the 2 lobes. Okay, what is the advantage of a 5/8 wavelength whip antenna for VHF and UHF if you're in your mobile? It has more gain than a quarter wavelength antenna. That is correct. The slide said approximately 2 dB, but yeah, I've seen 3. So here's your takeaways for this lesson. Horizontal dipole. Let's see. Horizontal dipole is horizontally polarized. Half-wave antenna radiates broadside to the radiator. Be sure to remember how to calculate the length. Be sure to put in the velocity factor to get your answer closer. Shortening increases resonant frequency, so you make the antenna shorter, frequency goes up. Quarter wavelength vertical radiates horizontal. Quarter wavelength vertical radiates horizontal. Length is a quarter. Remember that formula. Remember, if you put it wavelength over 4, it's a quarter. Wavelength over 2 is a half. Antenna loading electrically lengthens antenna loading electrically lengthens and is usually inductors, can be capacitors, but it's usually inductors. Directional antennas concentrate signal in one direction. Gain is increased signal in a direction relative to reference. Okay, so you don't actually create more power, you're just concentrating it. Yagi is the most common. Handheld VHF, UHF rubber ducky is inefficient and inside your car. The shielding of the car is further reducing it. Mobile 5/8 inch whip, or I'm sorry, 5/8 wavelength whip has more gain than a quarter wavelength. And stop recording.